Are we recording on here?
I believe we're recording.
Cool.
Yeah. We are recording. Thank you very much for that extensive welcoming. So, John Lennon, once again, missed the opportunity to put any John Lennon music in here. We were discussing before this that I should have just had like one song on repeat, very, very low in the background throughout the entire presentation. Me and this mic have always had like a bad relationship, so I'm going to try not move. Can everyone hear me? Yes? No? Cool. If I don't move, then maybe this will be better. I tend to run up and down. Cool. So let me just start with our focus. So explaining neural networks is always a bit of a nightmare because I don't have a board and I don't want to bore everyone with lots and lots of maths. The maths actually isn't quite boring, and it actually isn't as hard as you think it would be, but that's not what we want to focus on. So what I'd like to focus on is getting the intuition of what neural networks are about. On top of that, let me introduce you to some of the tools. We've made amazing advancements in the tools, thanks to Google. You've probably heard of TensorFlow, and perhaps Keras, which is the one we're going to be focusing on. And we'd like to have some fun, which is why we're choosing something fun, like mimicking John Lennon. In terms of my outline, I'm going to go through the basics of what a neural network is. We're going to involve ourselves in the process of a writer and how that's different from, the way we think about other sort of predictive models. I'm going to introduce you to Keras, which is the Google tool we'll be working with. And then we're going to make our little artificial beetle. Cool. So the basics. Quick hands up, who has built a neural network? Cool, so this beginning bit's going to be a bit boring for you, or maybe it'll be a nice refresher. For everyone else, I'm going to try, like I said, if you're not gathering the hardcore stuff, like focus on the intuition, that aids you a lot in this process. So the basics, when we're talking about neural networks and machine learning, we're usually talking about what they call the supervised model. So given a set of known data, how can we use that data to predict future events? So let's say we're going to try and build something to predict whether people are going to default on loans. So you've got perhaps a couple of inputs, things you know about a customer that defaulted or didn't. You've got salary, age, debt, credit score. I made up that credit score. I don't actually know what they use. I made it out of 100, why not? And then whether they defaulted on the loan that was given to them. And we call each of these patterns or observations. So like I said, let's predict we'll predict loans, predict whether someone's going to default on a loan. So should we give this person a loan, essentially? So here we'd have, cool, we know the salary of someone, we know the age, we know what debt they currently have, and we know their credit score. Are they going to default on the loan? That is the idea of what we want to do first. This is just conceptually. Later on, we're going to get to how we're going to translate all this into natural language processing and John Lennon. So ideally, the way you're going to do this is you start with some sort of, we've got some customer details that we know. We want to feed that to something, I don't know, some people like to call it a magic box. And out pops whether they'll default on the loan or not. That magic box is just a function for all intents and purposes. It's some linear algebra. It's not very difficult. It's finicky and the process is a bit annoying, but it's actually not too bad when you look at it. So let's try to be clever people. If we were going to try to do this as human beings, how would we as a human go about thinking about this? So we might look at this new person at the bottom here and be like, oh, okay, he seems similar to that guy, similar salary, similar age, similar debt amount, similar credit score. Maybe it should be yes. And then maybe we'd have a lot more data probably than these 5 patterns, and we'd find someone who contradicts that a bit. We might adjust. Okay, well, maybe age is more important than their credit score. Maybe salary is more important than the amount of debt they have. So if we were trying to be really clever, we'd probably come up with some sort of mathematical function where you've got a whole bunch of inputs, and we'd rank the inputs. We give them kind of weight. So maybe salary contributes to 0.3 of the likelihood that they're actually going to default, and age 0.2. These are all just made up numbers. You can see these as weights. We're kind of weighting each of these little attributes. And you'd kind of sum these all up or do, they call it a dot product, but it's essentially just multiplying things and adding them together, a weighted sum. And we get a number out, and then you'd say, cool, if that number is less than a threshold, then they're not going to default, and if it's greater than a threshold, then they are. And that's essentially what a neural network is, in very simple terms. That would be actually more of a linear regression. And the idea is that machine learning tries to adjust those weights automatically to something that will actually give you the correct answer. If we're looking at a neural network, it looks a lot more like this. So this is a 2-layered neural network. Might seem a bit scary, but you can see we've got some inputs. We're going to predict some output. And we've got these weights. I know they're drawn in as lines, but essentially they're just 2 matrices. This boils down to 1 matrix, and that's actually just another matrix. And you've got some sort of function that makes it non-linear, which once again you can look up afterwards. So how do we train this thing? So we've got this kind of idea here. We get what we want. We're going to put in some values we know, and we're going to get a prediction out of it. How are we going to train this neural network to use the information we know to give us that? So we've got this training process, and the idea is we feed in known data, this past data that we have, and we know the answers to. So we know if someone defaulted on a loan that we've already given them. So we look at our past data and we say, cool, well, we're going to use this to predict what could happen in the future with other people. So we feed in our training data into our function. Our function makes a guess based on these weights that are randomly initialized. Checks if our guess was correct, because we've got the answer. This is a known pattern. If it was correct, then we go, cool. If it wasn't correct, then, well, let's adjust those weights magically to make sure that the next time we do this, the correct answer is a little bit more probable. And they do that through a mathematical process called backpropagation. Once again, sounds very fancy, is a little bit scary when you look at it, but not too much to worry about. If you're understanding the intuition so far, then you're on the right track. So quickly run through the process again. You initialize the weights. The weights are the little things that link the input to the output. Initialize them randomly from the beginning. You feed in an input and make a guess. You calculate the error, so the difference between the target and the actual guess. If the target is far away from the guess, then you need to adjust your weights a lot. If it's quite close, then you probably only have to adjust them a little bit. So you adjust your weights to make the correct outcome more probable next time. And you would repeat this, I've said image there from an old presentation, but you repeat this for every single pattern, and you do this over and over and over again. And you'd find this process over time results in a model, most of the time, if your data is sufficient, will result in a model that can actually predict something like that. So if you look at this, you'd input some sort of known data, and it would make a guess, and it would say, let's say it's a no default, but we knew from our data that that person was going to default on his loan. Then we'd actually change these little weights, which are the little things in between here, so that next time when we push this through, like I said, it's just some linear algebra, it would more likely end up the prediction that you want. Each line is a weight, as I said. So that's my very quick skim through on neural networks. How are we feeling? How's our intuition feeling? Are we kind of following the concept? Like, you don't have to understand the detail, but if you understand that we have some maths and we can adjust it so that it makes better guesses over time, then you're already on the right track. So let's talk about natural language processing. So if we're going to build an artificial John Lennon, we need to figure out how he's going to write these lyrics, right? And natural language processing is simply the ability for a computer program to understand human speech as it is spoken. And we have a lot of common uses for this. So one that they consider solved is sentiment analysis. So that is whether something is positive or has a positive or negative sentiment. So you can't see in that picture, but this I think was just before the US election, and Donald Trump has a slightly negative connotation. So I wonder which echo chamber they were in there. Another thing that they're looking at is question answering. So we see this a lot in chatbots, which are becoming very popular, particularly if you're working in consulting. Everybody needs one and everybody wants one. Sometimes I think to their detriment, but never mind that. So question answering is becoming very popular. And then we've seen amazing advances made by Google, in particular with their machine translation. And they've actually been outstanding. So one of the things they actually were able to do was they trained a neural network to translate from English to Spanish, and they trained a neural network to translate from English to Portuguese. And then using those neural networks, they were able to translate from Spanish to Portuguese. So they never had to go through this middle step. They just positioned their neural networks correctly, which has a lot of really cool implications, which I'll talk about one day. So let's talk about the writer. So as you've seen from our previous neural network, it had quite a big limitation, which was never highlighted, in that, whether you should be given a loan is probably quite dependent on the time in which we're giving you the loan. Like, how is the market doing, etc. What's the economy like? And the one thing your basic neural network does not understand is the progress of time. The idea is when we're speaking in sentences, by the time I get to the end of the sentence, we haven't forgotten the first, and it's only by the time we get to the end that we've built up this full meaning. A neural network, if we fed it a word, it would maybe predict another word, and then it would forget about it, and next time we feed it a word, it will have forgotten about that. So our standard one would not be suitable. So what we want to do is the following for our artificial John Lennon, is we want to train a neural network to do this. Given a set of characters, in our case we chose 40, predict the most likely next character. So all the lonely people, where do they all come from, if you know the song? So the next most probable letter would be a C. And after that it would be an O. And after that it would be an M. And we're going to train a neural network to be able to, given a set of input, be able to predict the most likely character. And this seems a bit strange to us. We don't think in characters, we think in words. And it's true. If we go further into natural language, you'll figure out there's a whole set of research that actually works with words. But for the case of simplicity, I'm going to stick to just using characters. And you'll see how far we can actually get by simply doing this character prediction. Cool. As I've said, a standard neural network does not understand time. But one of the things of deep learning, I'm sure you've heard this buzzword thrown around 100 times, but one of the algorithms, the key algorithms in deep learning, so to say, is called a recurrent neural network. And a recurrent neural network is built to understand the progress of time. So let's shift our brain and look at a neural network like this. I did this because this is a really, you should go check out my source at the bottom there. It's one of the best resources you'll ever get in understanding recurrent neural networks. And the idea is you start it with an input. This is a normal one. You start with an input, you've got all that jazz in the middle, as I've shown you, and you get an output. A recurrent neural network, you feed it an input, and it predicts an output. And the next time you feed it an input, it remembers the previous thing you inputted to some extent. And it uses that to kind of adjust its prediction of what the next thing will be. So if you think about the way we write words, it'll be able to predict, or hopefully it'll be able to predict each letter as we go. What's clever about these things and the way they build them these days is they can actually choose what to remember. So the type of neural network we'll be using is called a long short-term memory, and that actually remembers or tries to remember what it needs to be remembering the most from the past. So the word was probably not important, but lonely was perhaps important, or the L or something like that, whereas the space might not be as important. So this all sounds fun. But let's look at the training data. Maybe that'll make things a bit clearer. So the idea is we look in a sliding window. So over here we've got a window size of 34 characters. So this is what we'll give our neural network. And we'll ask it to predict the next word. And then we'll shift it and say, cool, well, now that you've predicted that one, we'll ask you to predict the next one. And now that you've given that one, we'll ask you to predict that one. So our training data looks a bit like this. So we basically break these sliding windows of text into input, target, input, target. And we do this with a very, very giant corpus. So you'll look at something like, we're going to use Beatles lyrics, but you could use something more general, such as the Google News database, which is huge. And that's just loads and loads of articles. And you'll basically break it up into these windows and predicted characters. So this window should result in this character, and this window of text should result in this character. So this diagram was meant to make things clearer. Upon looking at it again, I'm not even sure. And what I'm trying to illustrate here is that you feed in a C, and that has some input, and then you feed in an A, and it uses some of the input that it got from the previous one. And you feed in an N, and it's using both of their input from the previous thing. And eventually, by the time it gets to even, it's hopefully figured out, or got to Eve, it's figured out that the next letter is N. Cool. So we're going to train our artificial John Lennon using a character predictor. This is what they're called, character predictors. We're going to use a song lyrics dataset from Kaggle. Kaggle's amazing if you're into data science or you want to get into data science. This is an amazing place to start. It's also, Google acquired it, I think, last year. And it's really awesome. They're basically competitions where they give you data sets, you get to download them, build a model, submit your model, or submit your predictions, and then you can win prizes. And it's a great training ground, I think, if you're someone who wants to become a data scientist or a machine learning expert. And our particular type of recurrent neural network we'll be using is called a long short-term memory neural network. Cool. How? Another question. So out of those people who built neural networks, who coded them in Java or C++ before Python existed, really? Who remembers the pain? So back in my day, which was, I think, about probably 6 years ago when I studied, there wasn't, if you know, the libraries were out there, I didn't know about them. I was at university and I was using C++, and I was like, cool, we have to code a neural network. We had to code all that maths ourselves. We've come very far in 5 years or 7 years, and this quote, being able to go from idea to result within the least possible delay is key to doing good research. And this is a quote from Francois Chollet. And Francois Chollet is the guy who created Keras, works for Google. And this is a big difference from trying to manually code all the maths yourself. So Keras is simply a high-level neural network API. It's written in Python. It can run on top of TensorFlow, which you've probably heard of. It's Google's AI library and neural network library. TensorFlow is a type of library that makes you feel stupid. So if you want to feel stupid, go open up some TensorFlow code. Makes me feel stupid. One of my favorite researchers works for a company called Fast.ai. Their caption is making neural networks uncool again. So they like exploring neural networks in uncool technologies like, you know, on Windows with C#. But one of the things they also really like is Keras, because it demystifies what TensorFlow had created, which was, you know, making some things a little bit more complicated than they needed to. And what's great about Keras is you can sit on top of TensorFlow, or you can sit on top of Theano, which is Stanford's API, which is actually a lot nicer than TensorFlow. It's just a bit older and a bit slower. Or CNTK, which I can't remember who that is, but it's also quite nice. So all that talk and all that diagrams and all that maths that I didn't even get into boils down to this many lines of code. So that first neural network that I kind of showed you would look a little bit like this. This is a pretty stupid one. The first 4 lines set up the architecture of your neural network. So what we're saying is you've got 2 layers, so 2 dense layers, fully connected layers, like I showed you in those diagrams. And .compile just puts it all together. You specify what your loss is, which is how you calculate how to adjust things. You specify some metrics you want to track. You specify an optimizer, also some maths that is important but isn't important for this. And the next 3 lines are just generating some random data. And the last line is how you train it. .fit. That is it. So for anyone who's coded a neural network, this will probably make you go blind with rage. 5 lines to do what used to take you pages and pages and files of code. So we're going to go do a little demo. We're going to run through the code. I'm using Python 3.3. Up until yesterday, I was using Python 2.7 because I suck, and I finally decided to advance myself. Using a library called Pandas, a really amazing library if you want to get into data science. Unbelievable, actually. A data frame is a really powerful object. I'm going to use Keras, as I said. You can use TensorFlow or Theano. I think I'm using TensorFlow. On this PC I'm using TensorFlow. And there's another little library there which just allows you to serialize the model. Before I get to the demo, I think this went into too much detail. But once again, we take our input data, which is different songs. We combine that into one big text or string field, which just has everything, all the lyrics by the Beatles in it. Then we separate that into little windows. So like I said, windows of size 40, predicting the next character. We convert those characters in what they call one-hot vectors, and that's just a way of viewing a character. So if There are 64, are there 64? 64 characters in uppercase and lowercase, I can't remember. But you basically convert it into an array, where let's say if you've got an array of 64, which I think is all uppercase and lowercase characters, an A would be, the first one would be 1, and everything else would be zeros, and a B would be, the second one would be a 1, and everything else would be zeros. So it's just a really easy way to translate characters to something a neural network would understand. We're going to set up our architecture for a neural network, which, once again, I think it's maybe more, might be 4 lines, 5 lines, 6 lines. Going to fit the neural network to the training data, a little bit more, but not that many more lines of code. And the majority of the code is actually getting some output out of it. And we're going to give the neural network a 40-character seed, so a seed of like 40 characters, and then we're going to resample it and say predict the next character, and we'll take that as the new window, predict the next character. And we do that until it builds us a song, quite amazingly. Let me switch to the demo. Alrighty. Can we kind of see that? Ooh, I need to scroll up. So this is something called Jupyter Notebooks. Has anyone used Jupyter Notebooks before? All our Python devs. This microphone is misbehaving. So Jupyter Notebooks are wonderful. It's a way, runs in your browser. You can also get a IDE version of it. But the idea is that you can run these little paragraphs of code, which is really great if you're doing demos or if you're doing something really interactive like data science. Cool. So let's train a recurrent neural network to write songs. So first of all, we're going to check our corpus. Every time you stand in front of the thing, I think it disconnects. I'm figuring it out. Stay there, don't move. Okay. Cool. This is not scrolling. Boom. I will use the little scrolly thing. Okay. So checking out our corpus. So our corpus is called songdata.csv. This is a little bit of pandas code. That's all the way jumped to the end. Oh no, nothing is scrolling the way I wanted to. Okay, there we go. I had to zoom in a lot so you guys could see. So we've actually got some output, but I'm going to run it. Show you cool, that's our song data. It actually contains songs from hundreds and thousands of artists. So we've got some songs from ABBA right at the top of our data set. Artist ABBA, songs, Bangarang, Banger Boomerang, I haven't heard these ABBA songs. Gives you a link, and then it's got the text, and this is cut off, but it actually has the entire lyrics to the entire song there. So let's have a look at what's in here. It keeps jumping up awkwardly. Oh well. So our corpus length, that is the entire of all the songs combined together, is a lot of characters, and we've got 50 unique characters. If you'll see, I've got written a little line there that actually lowercases them, because by having more cases, we actually give more source space to the neural network, and we don't want to get away from that receiver. Cool, so this is great. This is us filtering, saying we just want Beatles songs. And that's jumped forward. So now, in our little data frame, we go df.head, gives us just the Beatles songs. Across the Universe, And I Love Her, and all our little lyrics are in this last one called text. So now I need to create our corpus. Like I said, our corpus is just combining them into one big text field. So here I basically concatenate them all, lowercase them, and I'm going to output the corpus length. Then I'm going to truncate them. And the reason I'm going to do that is because if these get too long, then it takes really long to train. Ideally, it's really cool if you can train on the entire set. It's usually recommended to go above 1 million characters if you can. It gives you a good sense of the language, apparently. Cool. Let's run. It's already run there anyway. Cool. So now our corpus length is a lot shorter. My truncation didn't even matter because it's at 1 million. No wonder this neural network is stupid. Cool. Now we're going to create these overlapping windows. So this is an annoying little thing of code, but essentially it's just running through all the text and taking little chunks of it and predicting the next character. Then it's shifting 3 characters on, taking a chunk of 40 characters and predicting the one after that. And it creates up this entire little set of sequences, and we end up with 54,000 sequences. So 54,000 training patterns where we have a window. Given the window, we want to predict the next character. Here's some random code we don't have to worry about. So this generates the one-hot vectors. This is on GitHub, so you guys can check it out afterwards. And here's the Keras part. So up until now, we've just been doing input and some transformations, and we haven't even touched the AI. Here is the bulk of the AI. Those lines. You create what they call a sequential model. That's just a way of specifying the neural network. We create some long, short-term memory units. We tell them the size of the input shape and how many units we want to have. We have one final layer which says, cool, predict which character. So you can see it's the length of the characters or the number of unique characters. We give it some sort of activation. That's just a function you apply at the end. And we compile it with what they call categorical cross entropy and an optimizer called Adam. Once again, welcome to Google afterwards. Cool. Well, that was hard. Put model, compiling model. Now we've got that model sitting in memory. This is a little sample function. I should have moved it lower down. I ran it. I'll explain it later. Now to the training. So I've done a generator. If anyone knows Python, they know generators are basically a clever way of doing loops. So looping through a very, very large data set without having to load the entire data set into memory. So you can load 100 patterns, and they've got this great construct called yield, which allows you to kind of exit halfway through the loop, and then when you return back into the loop, you return at the point you left. It's really odd, but really cool. So I've given you the 2 here just so you can see. If you weren't going to use a generator, you could just say fit, and you could just say get data. So then you've got, cool, given some sentences and some characters, X would store your windows, your little set of characters, and Y would be the thing you're going to predict next. Cool, so you'd run that, and I could run that, but we'd be here for 2 hours. That's about how long it takes to run. That's with actually only 10 epochs, and what you want to do is about 30 epochs. An entire epoch is running through all the data 30 times. So I can run that and then stop it so you can see what it's going to do. It's going to start doing that. And 1 epoch is going to take 13 minutes. So let's not. So let's stop it. Great. I cheated, as one has to when doing demos, and I saved one. So let's load it in, as simple as that. It's been loaded, it's complaining about some nonsense. Don't worry too much. And this is actually, it's done, right? So you saw there was a lot of setup, and there were about 7 lines of neural network Keras code, and now that bit's done, okay? That was it. So what used to take lines and lines and pages and loads of head breaking and floating point errors and things that shouldn't be experienced is now 7 lines of Keras code, which is quite amazing. So these are all just little examples of seeds. I told you we seed it with 40 characters, and it predicts the next character. So, or predicts it uses that as seed and predicts the next one, and then it uses the previous 40 as the new window, and then predicts the next one. Hopefully, I keep explaining this. I hope it's getting across. So I've got a whole bunch of samples we could use. 2 first ones I made up once, and then I've got some quotes from some important women in tech who we should know about, and we can use them as seeds. So we've got Anita Borg, Grace Hopper, Radio Feldman, and Marissa Mayer. So who would we like to use today? I've got Marissa Mayer there because I was talking about women in tech, I think. So she said the number 1 most important thing we can do to increase the number of women in tech is to show a multiplicity of different role models, which I agree with. Very? Grace Hopper. We're going to do some Grace Hopper. Also, she's queen. I love Grace Hopper. Great. So what we're going to do is we're going to seed our artificial John Lennon with Grace Hopper. We're going to give the first 40 characters of this and ask John Lennon to write a song based on that. And that's essentially what this code does. I can show you a little bit. This is just a run to show you what the data looks like. the horrible data. So this is given our little window X. That's our window converted into numbers. Actually I think this is the prediction, so this is the likelihood. So basically, let me explain this bit a bit. It'll output a probability distribution. So it's going to output, cool, it's 50% likely to be an A, or the next letter is 50% likely to be an A, it's only 2% likely to be a B, it's 0% likely to be a C, it is 30% likely to be a, I don't know, a K or something, and it has this probability distribution. And what you can do is either take, cool, well let's choose our next letter as the most likely one, which in our case will probably be the A, or we can kind of give it a bit of variance to say, don't always choose the most likely character, sometimes choose the next likely character. So instead of choosing the A, choose the B, which is slightly less likely. So that's what our sample does. And this does that process of shifting the window, feeding it back in, shifting the window, feeding it back in. I can't remember if I ran that, I did. And now you can see our beautiful John Lennon. And this may seem a bit stupid, I'll read it out actually a little bit. No computer is ever going to ask anew. I know the strength in my bull. They say it anew, that you had to see. I was the pain to the one, the shadows and the trail. So it's a bit stupid, but that's all right. We didn't train it for very long. And to be fair, we only gave it characters, and we introduced some randomness to say, don't always choose the most likely character, just because I can demonstrate. If you do that, I think the entire song always says, I want you to know I love you, which I think I will demonstrate because that's fun. And it's actually written a whole song for us. The stars I know the rain, the stars I kiss my heart. We just gave it characters, and it knows how to do words, it knows how to do verses, it knows how to do choruses. Sure, it doesn't make sense, but like I said, we gave it some randomness, and all we fed it were characters. We didn't teach it about words, we definitely didn't teach it about kissing or rain or love, and it can still do this. That wasn't that many lines of code. So, who would like to give me a quote? Would you like to try someone else? Would you like to adjust our variance? Who's next? Who on a list? Me choose. I'm going to go with, let's go with Marissa Mayer. So, I actually looked up these quotes just before I went on. Actually, no, Radio Pullman. I'll call her Radio Pullman, that's her name. But Pullman was one of the key inventors of Ethernet. So she's quite a queen. And I'm going to have to run that again. And wait a little bit. The world would better be a better place if morning. The start I want to be the store. That is what I got to get it. I think the best time I ever ran this, I ended up with a neural network that just went la 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 la, but repetitively for paragraphs. It was great. So that is how you do that. And this is just characters. I think in the next week I'm going to get round to doing it with words. They've got this great concept called word vectors. Word vectors are also one of Google's creations. A guy called Thomas Mikolov invented them, and they kind of capture the semantic meaning in a word in a very large vector space. And they're very powerful. Word2Vec is the name of the technique. So I'll post that, and we'll give it some more context, and that should be able to teach it that it only tends to write about love and songs, which, to be fair, has already learnt out. But maybe then it'll get some grammar too, which will be great. Cool. So a little bit back to our presentation. I hope you enjoyed that fun demo. I always enjoy running that neural network. And if there's something you might have picked up, I didn't read through it all, but there's no continuous story. It doesn't really know from one chorus to the next chorus what's happening. Due to the random sampling, the words are always valid. And I'd like to show you this story. This is a sci-fi short film the script was written by a neural network. They fed it a whole bunch of science fiction and horror scripts, and it wrote this, and it's got Thomas Middleditch from Silicon Valley, who you all probably know. And I'm just going to play you a snippet out of it. Can leave it like that. Give a nice intro. So that's a whole list of the things they fitted. So I'm going to jump in halfway. So it didn't only write the dialogue, it also wrote the actions in between and what would happen. So let's jump there. Oh, there's some sound. Ooh. Can we turn the sound up?
That was the one with...
Let's try again. I'll just put on the subtitles if I can. If it would let me, Linux. There you go. And then you can see, mostly, how ridiculous it is. I don't know why it's not working. I am plugged in. It is on, so if I do that, it's on. I can plug it in now. Spits out an eyeball. Oh yeah, it was coming through here, and not that side. But I'll share these on Twitter. Otherwise,
yeah, I know that thing. You know, who's your said, really? I don't know. I don't know what you're talking about. That's right. So, what are you doing?
I don't want to be honest with you.
You don't have to do it obvious.
Sure. I don't know what you're talking about.
I'm missing you too.
What do you mean?
I'm sure you wouldn't even touch me.
I don't know what you're talking about.
Principle is completely constructive at the same time.
All about you to be true.
You didn't even watch the movie with the rest of the base.
I don't know.
I don't care.
I know. It's a consequence. But I really need to know about the presence of the story. I'm a little bit of a boy on the floor.
I don't know.
so that's a sample, but you should really go watch the whole thing. It's great. I hate it when Linux does this. All right. So let me go back. Let me F5. Damn it, I wouldn't want to go to this slide yet. But what I wanted to say is we've got a couple of problems still with what they call these long short-term memory neural networks, is that they don't actually get the full story. They're good at doing the last 40 characters and they can use that to remember, but because that's all they really know, they eventually lose memory of the past. So it might remember a little bit into the past, but it doesn't remember that far. So it maybe can construct grammatical sentences even, but it can't write a story. It doesn't know the plot. It can't construct a climax and an ending and things like that, which is a problem. So because it's Women's Day, and this got pointed out to me on ZA Tech, apparently John Lennon was a woman abuser, which is a bit sad because he was one of my heroes. If you look at what he says about it, it's definitely something he sincerely regrets. And he's actually admitted to it. He says, that's why I'm always on about peace, you see. It is the most violent people who go for love and peace. Everything's the opposite. So what he's basically saying is that he has such a violent passion and he lashes out, if you read some of his quotes. And that resulted in him hitting his current wife, which is simply unacceptable. And we shouldn't disregard and not listen to any of the Beatles anymore. I don't think that's the right way, but we should acknowledge that there are some villains in our midst. And some of them are very important people, and as we've seen in recent news, they often are very powerful people, and they shouldn't be getting away with stuff like that. And yeah, so that is the end of my talk, on a little somber note. Ask me questions, I like questions, mail me over there, tweet me over there. I'm doing another talk at the Future Data Meetup if anyone wants to come through to that, or I'll be by the beer. Thank you very much, and I hope you have a wondrous Thursday. Thank you so much, Jay. That was awesome. I really enjoyed that. I think it's the simplest explanation of neural nets I've ever heard. So I think I finally clicked to something now. So that's great. So do we have any questions for Jay? As always, it's like, oh my goodness.
But I like him.
So much stuff. Okay, any questions now? Yeah, one question, yeah.
So you said you're doing data science and these kind of neural nets and everything at work.
Yeah.
So who are your clients and what kind of systems do you build?
Cool. So
For the kind of deep neural network side, that is obviously a startup who would be willing to take that kind of risk and would have that kind of problem. They're called Kaleido, K-A-L-I-D-O, and we're using it for natural language processing. Pretty damn cool startup. You should check it out. Other clients usually prefer more traditional methods. The reason being neural networks are a little bit of a black box. And business doesn't like that. They like to verify everything. So they tend to prefer more traditional kind of things, older, like normal linear regression, random forests, the trees and stuff, which you can actually look at. And there it'll be insurers and banks and basically anyone who needs analytics, right? And there is a bit of a process to convincing them that they need to use a neural network. One thing I should say is that very rarely do you get the opportunity to actually code something like this yourself, and very rarely do you often need to. So if you look at something like a 0ML, you can do all this with like a couple of clicks. You don't even have to write any code. It's actually quite amazing. And usually you'd use cloud providers. So Google's ones are really good. So Google Vision, even if you're doing images, they've also got some decent text ones. And you very rarely have to touch the nitty-gritty bits. So often the clients would prefer to go for, and I believe that makes sense, the well-tried and tested cloud services. There we go. Got a Google mention in there again. It's like 3. Does that answer your question?
Yeah, so I think the tech is great and everyone wants to be doing machine learning and all of these cool things, but we just don't know if it's happening really in South Africa and who the companies are that are getting it. We work in banking and all these things, but are they applying it?
I'd say they are, and I'd say what's really great, so when I started I always wanted to sell AI to everybody and nobody wanted it, and now it's a buzzword, so everybody wants it. They're like, our competitors got it, we need it now. What does it do? I don't know, but I need it, which is a problem in itself that you have to deal with. But basically everyone wants it now. For the first time you can kind of go, cool, well, here are some AI and the kind of game changers in those companies, any of them, whether it be engineering or medical or whatever, are making those changes and actually doing it, or at least trying it out, And when they see the impact of it, they often do go full speed ahead because it really differentiates them from other companies in South African space. Yes. Yes.
So do you think AI will take over developers?
Not for a while. I think I've actually got a really cool one where you give a neural network a image of a website and it generates the HTML and CSS for you. Pretty scary, considering what we do, but also a little bit contrived because they actually kind of teach it about the elements, so it knows that you should be using these elements in the design. I've seen another cool one where they take a photo of like basically a whiteboard with some prototype drawn on it, and then it generates the app. But once again, it'll only generate it in like a certain number of components, and it'll definitely always be material design, and it'll probably always be the same color. But so I think we've still got a way to go, particularly when it comes to generalization. We're really good at training for specific tasks in a very specific, limited way. So I think we'll still be the last to go. I think some of our very basic, some of our the last to go. Accountants first, developers last, apparently auditors last. But yeah, so no, not yet. I think some bits will be taken over pretty soon. Some of the annoying bits we don't want to do, and I'm okay with that, frankly. Like, I don't want to write CSS. No one does. Yes. Yes.
Yeah, so when it comes to UX, obviously, let's talk about chatbots for a second. You mentioned
Sure.
earlier, everybody wants a chatbot. Nothing more annoying than a chatbot that can't answer you.
Yes.
And then we have obviously the human element and biases. How do you see that kind of being handled in the future?
So by human element, you mean?
So, like for instance, with Google, if you type certain things in, it comes out with something very basic, right?
Yes.
So how do we kind of predict that, and where do you see it going? If we'll ever get to the point where we can have a real conversation with the bots and it will give us an honest answer, is something we're looking for? Where do you see bots going? Are they going to die, or are we going to?
I'm not going to lie, they are a buzzword and they are what everyone wants. But we've had bots already, like they're coming and going. A lot of bots these days don't even use AI. Bots that can't answer what you want these days is usually a result of a bad UX actually, that they didn't understand the flow. And AI can't actually get past that, at least not yet. It doesn't understand context. It just knows small things, so how can it understand where in a flow you are? Whereas humans can construct that. In terms of ethical issues, thankfully, at least in the past year, there's been a big rise in discussions and researchers talking about ethics in AI and making conscious efforts to try. It's quite hard because the stuff, AI is trained on data, you can see that. It's data humans have generated. Think if everyone goes, oh, it's unbiased, it's data. No, it's human generated data. It's got bias embedded into it, right? And they've got really scary cases in the States where they're using prior data for convictions to predict sentences. So they're using like data on a person to actually, and it's happening, and I can't remember which state. I'll have to look at. They're actually using it. Hopefully they've stopped by now. But what it was doing was, if you were black, you got a larger sentence because that's what humans did, right? Like the judges were biased and they encoded that bias, which is frightening. We can't live like that. And I think until we get past that, we're never going to be able to use these systems for anything meaningful. So, is it a problem? A huge one. Should we trust AI with our lives? No, because it's just encoding our bias. Are we making leaps and bounds to fix it? Yes, I think we are, and we're paying, the research community at least, is paying a very, very large amount of interest, talking about it a lot, coming up with really good solutions for instance, in language, removing gender bias. You know, if you say nurse, it's going to assume it's a female, and you'll see the way the sentence predicts, it'll predict that. And they're coming up with really good techniques for kind of counteracting that. And as you say, it's really hard because the data's wrong. And will we ever get past that? No, I think it's always going to be a conscious issue and something we really should keep conscious. So the future of it, we're going to struggle with it for a lot of years coming. Chatbots becoming better at it, yes, I think that'll happen. I think it won't happen in machine learning. I think it'll happen in other areas of AI. That'll be able to kind of do the planning to control where in a conversation flow we need to go. Yeah, that's my random speculation. Sorry, got carried away. Did that sort of answer your question? Okay, cool. Yeah. Yeah, I will tweet it as soon as I update it to Python 3.3. So I've updated it, I just need to push that. So I'll tweet that, and I'll tweet the presentation as well. So if you want to look at anything that I've explained there too. Yeah, cool. Thank you so much.